Let's say you have to build some kind of monitoring dashboard. Maybe you need to gather logs, maybe you need to gather metrics from various sensors, maybe you need to gather error counts, telemetry from drones or from cars or from e-bikes, whatever it is. And so the obvious choice would be to just store the resource metrics in something like PostgreSQL. That's the obvious choice. It's already there. You just write into it, no problem. But 6 months later, the table has 50 million rows. You are trying to query for something like the average response time per 5-minute bucket over the last 24 hours, and you get a very slow answer. It takes you 8 seconds, 10 seconds, 15 seconds. Then you decide to add an index. This helps, but the table keeps growing, and then somebody else adds manual monthly partitions. Then somebody needs to write a cleanup job to expire all data. And finally, you have a bunch of engineers who did a lot of work in order to fight a problem that should not exist. You were just using the wrong tool. And the spoiler alert, the good tool for this is time series database. So let's talk about it. Welcome back to Think Design Work Smart. I'm Alex Bolboac and I'm coming at you from the Mosaic Work Studios, and today I want to talk about time series databases. Time series databases, like other types of databases, are tools specific for one kind of problem. And right now, as a general statement, if you want to figure out how to solve some of your problems, some of your architectural problems, you might want to look at the databases. We don't have, for a long time now, we don't have only relational databases and NoSQL databases and caching. We have all kinds of databases optimized for various types of things. We have blockchain, we have vector databases, we have time series databases, we have databases optimized for write, for read, for high distribution, like, for example, Cassandra. So there's a lot of different types of databases, and that's the most interesting part of software architecture right now. And I think if you pick the right database, you might solve a lot of problems in your architecture once they grow unmanageable. So let's talk about why this is useful. The problem isn't your queries, your schemas, your index. It's just that the relational databases are not optimized for this type of access pattern. You have, on one hand, if you are thinking about time series, you have high frequency sequential writes. Like maybe you write hundreds, thousands of pieces of data, of records per minute. And then on the other hand, you have time range aggregation queries. So you need to query for things like the average time for, or the average values for a specific sensor within a 5-minute window in the last 24 hours. And that's where things start to get complicated. And of course, you can make PostgreSQL or your favorite relational database work with this, but it just won't work as well as one type of database that's optimized for this. So what is a time series database doing differently? First, you have append-optimized storage. If you think about it, what you're doing with time series is that you keep adding at the end, and there's a sequence given by time. Now, maybe you will get from different sources data, and those sources will have different times, so they won't get perfectly in the order of the timeline, but it's close enough, right? So you have append-optimized storage, writes are sequential, which means you don't have random IO, you always write at the end, and there's no contention on existing rows. You don't have to worry that you will update past row with new data, right? This is already very important because it makes your databases work differently. Let me pause a little and say that one of my first projects in the industry was a database engine, actually. And I saw how structuring the database differently makes a lot of difference in terms of optimizations. And in that case, we had basically a NoSQL database before it was a thing. And what we are trying to do is to optimize it for report generation from a mix of data. And storing a big decision is whether you store data based on columns or based on rows, and this influences a lot of things in your engine. But about that, we can discuss other time. So first, append-optimized storage, back to our time series database. Second, automatic time-based partitioning. What this means is that you declare a time column and a chunk interval, and the database creates, manages, and queries across partitions transparently. What this means is if you are looking for data for the past 5 minutes, it will only look for, let's say you are partitioning for 1 week, okay? If you look for data for the past 5 minutes, it will only look through that week and not through all the table, not through all the 6 months. And this is done transparently by the database engine. Queries targeting a time range only touch the relevant chunks. You don't have to do this manually, you don't have to do partitioning manual, you don't have to do cleanup scripts. You have retention and you have expiry policies, which makes everything goes right. So if you think about logging, it's basically the log rotate policy. Then you have compression. This is very important. If you think about it, timestamps are sequential, so you already have a sequence of data. So basically you can compress that column because you know there will be, I don't know, the initial timestamp and then plus 1, plus 1, plus 1, plus 100 milliseconds and so on, whatever it is, okay? On the other hand, the values that you are storing don't change a lot because, well, depending on how often you get the data, but typically if you get the data often enough, you'll just have slight differences. Like if you measure CPU percentage or response times, or I don't know, the pressure in pipes, or it's unlikely that that will change suddenly. What this means is that you can compress those columns as well. And there are algorithms like Gorilla compression that can achieve 10 times better compression. So this means, for example, a year of metrics that would take 500 gigabytes in PostgreSQL might take 40 to 50 gigabytes in InfluxDB, which is a time series database. And finally, you have first-class time operations. You can do aggregations based on windows, so things like the average of that metric in the past 5 minutes. Or you can do statistics based on time intervals. Let's say I want to see the average for values over a 5-minute window in the past week, something like that. You have downsampling, you have retention policies that are native. So you decide what to keep, how long, and so on. And this means that you have two axes that matter. You have, on right side, high-frequency sequential inserts. It means that you can basically ingest a lot of data very quickly without the engine choking or doing anything unusual. And then on the read side, you have you can do last 10 measures, interval queries, averages, distributions, do statistics, do all kinds of queries. What's interesting is that if you do log files, if you compare it to log files are faster for writing because instead of going through a whole system, it just goes through the I/O and it just writes at the end of a file. So it's again append only. So the writes are faster if you're just using log files, but of course you cannot easily query log files, which takes us to the common pattern for using this. And this is ingest, store, query, visualize, or alert. So basically what you do is you can write into log files because it's very quick. You then ingest the log files. You can then query the log files in the time series database and then create visualization or alerts based on the data that you create, that you process. And the other option is to write directly in a time series database. Nothing stops you. So but you can choose basically between writing in log files or writing into time series databases. Now, in terms of concrete stacks, you can, a very common one, very well known, Prometheus and Grafana, used for metrics, application metrics, and for visualizing and creating alerts, visualizing trends, and so on. So that's basically used for monitoring particularly large distributed systems, microservices, cloud systems, all that. You can also use InfluxDB and Grafana. You can also use something like logs, Fluentd, TimescaleDB, and Grafana. So you have these stacks. And of course, you can probably, avoid Grafana or Prometheus and just use like open source tools and then create your own alerts on top of those. The sky's the limit here. But it's important to understand how this works, and it's not magic. It's just a good database, basically. And alerts are particularly easy to do with time series database because it's easy to do something like alert when average response time exceeds 10 seconds over the last 5 minutes. This is very trivial to do. It's very painful to do in a relational database like PostgreSQL or Oracle or SQL Server or whatever you are using, unless you are using a specialized engine for or storage for time series database. Some of these databases might have that. Of course, no technology is perfect. And the question is, there are two questions: when not to use them, when it doesn't make sense to use them, and when to start using them if you started from, let's say, log files or a relational database. When not to use them, you don't use them for complex entity relationships. If you don't have time series database, but you have time series database plus relations between the various metrics, then it gets complicated. These are optimized for writing at the end and not for writing a lot of relationships. Obviously, don't use them for data that isn't time indexed. So if you have just data, general, user information or accounts or orders, those are not time indexed necessarily. The orders are an interesting situation because in an e-commerce app, because orders could be time indexed for the goals of monitoring and reporting, but for the goal of delivering the order, they are not time indexed, right? So you can also think about it this way. There are two ways of using the same piece of information, but optimized for different goals. If you have low volume and your relational database just works, don't worry. You can just use it up to the point where you start seeing issues. and if you have a need for strong transactional guarantees, because these are just writing at the end and then you can query that. It will not give you the guarantee that if that thing is written, then that thing is written. It doesn't work like that. And we mentioned don't use them for low volume. What is low volume? So low volume is not about data size, it's about query patterns and write volume. If you are fighting your database with manual partitioning, cleanup scripts, slow aggregations, then the database is telling you it's the wrong tool, and then you have to switch to, or you should look into switching to a time series database. Now, what about the particular tools? Because we discussed the different advantages, disadvantages, trade-offs. Now let's talk tools. Lower switching cost. If you're already on PostgreSQL, you can use TimescaleDB, which is an extension to PostgreSQL. And I imagine for other databases, you have similar extensions that you can use, or maybe things that are built in by the builder of that database engine. Then you have InfluxDB, which is a separate database engine. It's purpose-built, it has a strong ecosystem, and it uses the compression we discussed previously, the Gorilla compression. You have Prometheus, that is monitoring specific, and it's a standard for Kubernetes. You have a newcomer called QuestDB, high performance, but it's newer, so it doesn't have as large of a community. And then you can run these as managed services, like buy from a company that is managing this service and is providing it to you, and you just need to write into the database. Or you can self-host some of these, or you can use the cloud native systems that provide similar tools. So you can use the AWS native services, or the Azure, or the Google Cloud, whichever are most useful for you. But in general, what I'd like you to take from this video is not so much about the database itself. What's more interesting is to remember this. For certain use cases, if you are fighting your database, it's likely that you are not using the right database. And for this particular case, when you are dealing with time series, if you are fighting your database, then maybe you should switch to a time series database instead. And personally, I don't care which one. Pick the one that fits your scenario best. But in terms of architectural thinking, choosing the right tool for data often leads to really good results. So what do you think about this? Have you seen this transformation with time series database? Have you used other interesting database types like vector database, or I don't know, blockchains, or any other types of interesting databases? Let us know in the comments, and let us know if you have any other questions, comments about similar or other types of architectural decisions, about AI in software development, or about cybersecurity. Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.